Welcome again. So today we will begin new method, that is the matrix pose method. This is an analogous to the direct stiffness approach which we have already studied in detail. This method is also called as the flexibility method. Here member forces are treated as the basic unknowns. So as against to the stiffness approach where displacements are considered as the basic unknowns. So here forces are considered as the basic unknowns. In principle, the method is very much similar to the classical force method, but is very much organized, and here we make use of all the formulations in matrix format. So basically what we'll be doing is we'll be step by step building up the force displacement relationships, starting with the members. Members could be beam elements or members could be truss elements, and by using this approach we'll be able to make up the total structural flexibility matrix. This is a sort of finite element approach. Let us have a quick glance at the assumptions. So first and the foremost assumption is that Hooke's law of elasticity holds good, and then we are dealing with infinitesimally small deflections. Then there is no change in length of a member for deflections normal to the length of the member. Principle of superposition holds good, and the last, that all members are inextensible. Now the last assumption is something which we have brought here. This was not there in the case of the direct stiffness approach. Similarly, all other assumptions which we have not covered in detail, they are valid as in the case of the direct stiffness approach. So here, when we are dealing with this method, we shall first assume the structure to be determinate so that we derive the basic framework. And once we have done it, then we'll extend the approach to indeterminate structures. Essentially, when we use the matrix pose method, we make use of the equilibrium of forces, we make use of the displacement compatibility, and then derive the force displacement relations, first at the member level and then finally at the total structure level. So basically these steps will be repeated in the case of the matrix force approach also that we are going to study. So what we'll do, we'll begin with the classical force method first, and then we will derive the formulations for the matrix approach, first for determinate structures and then for the indeterminate structures. Let us just review the conventional force method by using an example of a beam with fixed conditions. If we are trying to solve an indeterminate structure, the first step is to choose the redundants and convert the structure into a primary structure. For example, here we have chosen the two moments as the redundant, and we have also made use of symmetry to keep just single variable x representing both the end moments. So using the principle of superposition, we can now break down this problem into two parts. First part, the primary structure under the assigned loads, and the second part, the same primary structure under the action of the unknown redundants. Using the conjugate beam method or moment area method or any other displacement finding method as per our convenience, we can find the angle of rotation for these two cases. For example, for the primary structure under the UDL W, the rotation is say theta 1, and for the same structure under the action of the redundants, let's say the end rotation is theta 2. You can very easily derive that theta 1 is WL cube by 24 EI and theta 2 is nothing but XL by 2 EI. Now we have to use the compatibility condition. The compatibility condition is that because the ends of the beam, they are fixed, so there won't be any net rotation from the superposition of the two structures, that is theta 1 and theta 2 must be equal and opposite to each other. And this gives us the value of the unknown redundant, the end moment, as WL square by 12. So once we have computed the main redundant, the other unknown reactions, they can be determined simply by using the equilibrium conditions. So we can summarize these steps involved in the classical force method for the case of indeterminate and determinate structures. So if we are dealing with an indeterminate structure, the first step is to choose appropriate redundants. The choice of redundants can be different for different persons. However, the structure should be stable. Then we form compatibility equations and equilibrium equations. And the next step is to solve these compatibility and equilibrium equations and obtain all the main unknown forces. Now, in the case of determinate structures, we may not need step number 1 at all, and also we don't need to form compatibility conditions. So in the case of determinate structures, only the equilibrium conditions, they are sufficient. Now let us extend the classical force method into the matrix force method. So for this purpose, we will define the matrix of beam and truss elements. So let us begin with a beam element, and if we now see the beam element, we have two main unknown forces here, the two end moments. So because this is the force method, so here the forces would go on. Here we won't talk about the degrees of freedom, but we'll talk about the line of action of the forces. So we have F1 and F2 as the moments at the two ends, and then we have the displacements D1 and D2, the corresponding rotations as the displacements. So note that here we are also using a superscript M to signify that these terms, they are referring to member M. So we can write the matrix of the internal displacements of the beam element like this: D1M and D2M in vertical column, and these are connected to the member end forces by a 2 by 2 matrix, and this 2 by 2 matrix is called as the flexibility matrix of the beam element. So on the right hand side we have F1m and F2m forming a vector of the internal forces at the two ends of the member. Please note that here we are not considering the shears, because shears, they are related to the member end moments. So if we are able to find the member end moments, we can obtain the member end shears also. Similarly, we are not considering axial force here because the members are considered to be inextensible after we solve for the member end moments. So based on the equilibrium of the structure, we can determine the axial forces in various members. So we don't need to include them here. So now this 2 by 2 matrix, we are denoting it by symbol Fm, and the components are F11, F12, F21 and F22. So this is a symmetric matrix, and here F12 and F21, they are equal to each other. So we need not compute all the 4 elements, just we need to determine the elements F11, F21 and F22. Now before we go ahead, we need to obtain the values of the various terms of the flexibility matrix of the member, and for this purpose we'll use definition of the flexibility term Fij. Earlier, while studying the non-prismatic members in the direct stiffness approach, we had introduced the definition of the flexibility term Fij. So we are just repeating that. So basically Fij for a member M is nothing but it's equal to the displacement along the line of action of the ith force owing to a unit force acting along the line of action of the jth force, all other forces being 0. Note that here we have not brought the degree of freedom anywhere. So we will derive the members of the flexibility matrix column by column as we have done for the case of the stiffness approach. So now how do we use the definition of Fij to derive the first column? So we will follow the approach analogous to the stiffness approach. So what we'll do, we'll apply a unit force along the line of action of the first designated force. Then by definition, the displacements along the lines of the various forces, they would be just equal to the first column of the flexibility matrix. For example, here now this is the structure and we are applying a unit moment along the line of action of the first designated force. So please note that in the force method, just like in the case of stiffness method, we use the common term force referring to both the moments as well as the forces. So we have applied the unit moment, and by definition the rotation at this end will be equal to F11. And here we are following the sign convention that anti-clockwise forces and anti-clockwise rotations, they are positive. Similarly, at the other end, the rotation will be equal to F21, but considered positive if it's anti-clockwise. So naturally we can see here that at the other end, the rotation is clockwise. So the result will be minus. So by using the basic equations of the slope deflection method, we can find out that F11 is L by 3ei and F21 is L by 6ei, but with minus sign. Similarly, when we apply a unit moment at the other end, then we would be able to derive the value of F22, and that will also come out to be L by 3i, and we need not find out F12 because that will be equal to F21 from the symmetry. So for beam element, the matrix can be written in this form as L by 6ei can be taken as common, and inside the bracket we have 2 minus 1 minus 1 2, like the way we have shown. So this is the general flexibility matrix of a beam element. So it's also valid for a frame element, that is a column element undergoing flexure will also have the same flexibility matrix. Now let's derive the member flexibility matrix for a general truss element. A truss member or a link element has only axial force. It does not have any moment or shears. So we can draw the member under the action of the forces like this. So if the extension undergone by the member, assuming that the force is tensile, then that will be equal to L by EA. And here the sign convention is that tensile forces and the tensile strains or tensile displacements, they are considered as positive. Compressive forces and the corresponding displacements, they are considered as negative. So here we are designating the forces as F1 with a superscript of 1, the superscript meaning that it's for member 1. Similarly, if we have mth member, then we can change to the superscript as M. So here for this member, the 1 by 1 flexibility matrix will be just L by EA. So on the left side we have the displacement, and on the right side we have the member and force. So for the mth member, this can be just written in the same manner, replacing 1 by M. So in this manner, 1 by 1, we can determine the flexibility matrix of all the members which are comprising the structure. So this is applicable for beams, frames and trusses. Now we have to define something called as the collective flexibility matrix. So if we just lump all these individual flexibility matrices in a diagonal form and keeping all the remaining terms as 0, then this results in the collective flexibility matrix of the structure. For example, if there is a frame which comprises of a total of n members, then what we can do, we can assemble all the member and displacements as a single vector one by one. For example, here we are arranging the displacements of first member, then the displacements of the second member, then the so on to the mth member, and finally the nth or the last member. And when we arrange all these displacements in a single vector, then this is basically the internal displacement vector of the entire structure. This displacement vector is connected to the combined vector of the internal forces of the structure by the collective flexibility matrix. So we can similarly form the combined internal force vector running from member number 1 to member number n, just like we have formed the vector of the internal displacements covering all members. So the size of these two vectors, the displacement vector and the internal force vector, will be equal to 2 times the total number of members if we are dealing with a beam or frame kind of structure. If we are dealing with a truss kind of structure, then the total size will be equal to the number of members. So the collective flexibility matrix will be of the same size. The square matrix will have each row and column equal to 2 times the total number of members. So now we are forming the collective flexibility matrix. All we have to do is we arrange the individual flexibility matrices of the total n members diagonally, and we fill the remaining terms as 0. So here the remaining terms are 0 because this kind of relationship between the vector of the internal displacements with the vector of the internal forces is such that there is no inter-member coupling. That is, the internal forces of a particular member are related to the internal displacements of that particular member only, and no other member comes into picture. That's why all other elements, barring these 2 by 2 number sets, they are all zeros. And we are taking the term L by 6EI common outside the entire collective flexibility matrix because it's common for all members. In a compact form, we can say that we have to simply arrange all the individual member flexibility matrices in a diagonal form and keep the remaining terms as 0.